Hello, ladies and gentlemen. Welcome back to the VMware Networking and Security live stream. I am happy to be back this week, and we're going to be talking about one of my favorite subjects, the NSX DR and SR. Now, in the previous weeks, we've been talking about a little bit about the DR and the SR, the designated router and the service router, but we haven't really gotten in depth on it, on what it does. So today, and fair warning, it's going to be a bit technical. We're going to dive a little bit deep into the woods, here in the weeds, if you will. We're going to get into some configuration. We're going to get into some command line stuff, which, will be fun in the lab. So, I hope that you can follow along. I want you to be able to follow along, and we're going to preface it with a lot of things. We're going to go off of the design reference guide like we were doing yesterday. So I'm going to share that link so everyone can follow along if you want to. And then Paul and I are just going to have casual conversation about the DR, the SR. Feel free to ask any questions. We're here for you. We're here to answer questions. We love them, in fact. And yeah, without further ado, let me introduce my guest yet again. He's back for a fourth week in a row. Mr. Paul Mancuso, how you doing?
Hey, Andrew. Everything's great here. It's kind of hard not to be unhappy when outside it's gorgeous and 70-some degrees, actually almost 90 degrees, I should say, here in Florida. So Jeez. It's a beautiful day, but it's a perfect golf day, something I might actually try to get in maybe at the end of the day here, hit a handful of golf balls at the range, but it's gorgeous. Everything's wonderful.
Yeah, excellent. We're a little bit of a hot streak right now as well here in Michigan. We're 82 degrees or so, but it's supposed to really get a little bit cooler in the coming days. So personally, I'm kind of looking forward to it. I like that kind of cooler, like 67 degree weather. So yeah, 60, 70, that's about right. So
80, boy, that's our winners.
I know you're in Florida. You all have weird weather over there. It's just very strange. So, all right, everyone. So, like I said, we encourage questions from everybody. The guide that we're going to be going off of today is the same guide that we did last week. I'm posting it in the comments right now. It is the 4.1 NSXT reference design guide. And today we're going to be focusing on talking about the DR and the SR and where that is in the document. If you all want to know, I'm going to bring this up right now just so that everybody can follow along. Did I you know what? I closed out the document. Oh, how silly of me. Let me open it right back up on my screen. Here it is. And just to share it off so everyone can see, give me 1 second while I present this. Not a video file. That's just silly. Sharing my screen, and it's going to be screen number 2. It's this design reference guide that we're talking about here. So we're going to be talking about principally starting on page 72, actually 73. We're going to be talking about the single tier routing and the dual tier routing, the services router, everything. So pretty much from 73 all the way up to just about, I think we'll get to 89 or so, page 89. We're going to be jumping back and forth. So if you want to keep track of what we're talking about here, this is the document that we're talking about. So Paul, first off, let's start off with a very simple thing. My very first question. What is a DR and an SR?
All right. Well, we talk about the usage of NSX routing. We do have essentially a handful of elements that do need to be defined. And I think we've done a pretty good job of doing the basis of much of that in the previous sessions. But to get to your question right off the bat, the DR and the SR, the distributed routing component is the east to west. The SR is a services router interface. And it also represents, for instance, the services router interface to the physical environment from the virtual machine edge in the tier 0 abstraction itself. Remember, we talked about the fact that tier 0 is really an abstraction that references the fact that it does distributed routing as well as service routing. And the service routing is about 8 different features. In fact, that guide you mentioned has a detail of each of those inter services, such as the physical interface, the ability to do load balancing and NAT and things of all that nature. Those would all be service router services off of that. And then each of those might actually have some other sub elements that have to be configured in order to make them functional. So yeah, you could stream through the guide there and you'll see where there's an actual listing of what the SR interface or what the SR service.
Yeah, we're getting to it right now. Where is here it is right here.
Okay, yeah, sorry there. I can't read it. It's a little too.
That's okay. So essentially, the service is, just to be able to recap for everybody, we're talking about physical infrastructure connectivity like BGP routing. We're talking about NAT and DHCP server, VPN, bridge firewall, bridging, and the service interface, which actually we're going to talk about a little bit today. Paul and I, we were discussing that before the stream, and the meta proxy for OpenStack. So a bunch of different things.
Right. So when we speak about it and we draw this out in a limited scope here, so this would be our vSphere infrastructure. We'll draw it out on the southbound side once again. We'll use purple to represent once again the embedded NSX elements in the vSphere infrastructure host. So this would be our transport zones. And we're going to draw them as just a single transport zone. So that would be the east-west as well as the north-south. So the purple represents the transport zones themselves. The edge, of course, refers to the fact that when we draw out our edge, that's our tier 0 element. So in our edge, here's would be our tier 0 element. But when we say it's our tier 0, it's also representing a series of other components, because the edge in itself also represents the tier 0 as well as the tier 1. So when we talk about it, we have, a tier 0, and we also have a tier 1, assuming we're talking two-tier routing. If we're talking single-tier routing, then it would just be the tier 0 with segments off of it, and north-south routing ingressing into and egressing in and out of the NSX network virtualized environment, and logical segments that would be plumbed right off of the tier 0 edges themselves. All right. And then, of course, that would be distributed throughout each of the other hosts. So if we were to draw in the other host, the other hypervisor host in here, if we were to draw them out in here itself, what is to be understood is that there's a tier 0, okay, as well as tier 1 components in each of these. And I'm going to draw this out a bit bigger over here, but I was just drawing this out to symbolize the fact that there's tier 0 as well as tier 1 components in each of the hypervisors. It's just that the SR service, for instance, the actual SR link, okay, the SR service that's here, the service router interface represents our physical connection to the outside world. And then the interlinks between the tier 1 and the tier 0, we're going to discuss how they provide their interconnectivity for when communication has to come in and out of the north-south, and then, of course, be transferred on an east-west. Now, we've done a bit of this in the past, so this one here is meant to not just discuss what we've pretty much stated to some fairly granular sense in our previous session, but we're actually going to go into the lab, right? Is that right, Andrew?
That's true.
Go into the lab, and that's going to be that heavy, detailed, technical aspect that Andrew had mentioned at the beginning that we really want to show you so that you have an understanding of it. But the beauty of all of this is, and that to keep this in mind, because that's the focal point you should understand, is that the deployment of this is far easier than you would quite imagine, because there's a lot of inner workings that automate itself in the background as you're fabricating the edge and routed services throughout the infrastructure for NSX. So note that when we go into a lot of the detail, you're thinking, oh, how do I have to construct all this? Well, in essence, we'll talk a bit about that. So when we talk about you create the tier 0, you're going to make some judgment decisions at that time that you have to live with, and you have to understand that what they mean. And there are a limited few, really, because much of what you actually create at that beginning is manageable and configurable after that. There's just one or two, there's actually 2 elements that you have to be aware of at that beginning. It's really just IP domain space more than anything. And or usage, I should say. And the other elements that you will create after that, the tier 1, again, when you go through the wizard, it pretty much tells you and prompts you what you have to do. So assuming you followed the wizard in setting up the edges themselves and the transport nodes and things of that nature, when you start creating the actual routed services within them, it's relatively simple.
Yeah, I think, a very important fact, just I want to hammer really home what Paul said. We are going to get, like I said earlier, a little bit deep into the weeds here. Normally, we would like to focus on use cases and not like specifically one little feature, one little thing of NSX, but how it can benefit you. We will sprinkle that in throughout this series and this show today, but we really wanted to have one where we're actually going to get a little bit more in depth and a little bit more cutting into like the technical aspect, maybe the operational aspect. But this is the beauty of it, is while we're getting in depth and talking about it, the actual implementation and creation of this is all very simple, and it's abstracted away for you on purpose. It's supposed to be simple. But if you want to get into the weeds, we're about to.
Right. So these are the distributed routing components that I was mentioning. And then you have the north-south routing that delivers that into the east-west. And remember, there's obviously the tunneling endpoints that are producing the interconnectivity between the hosts and the transport nodes where they host the edge. So be aware that I'm not putting that in here at the moment, but note that that will always exist here. So the vSphere hosts themselves have the TEPs. And in the transport nodes, when we refer to the virtual machine edges themselves, the edge nodes are the virtual machines. Those are the ones that contain the TEP. The ESXi host, hosting them, as we mentioned before, might have some NSX components themselves, but that would also mean that not only are they hosting the edge nodes, they're also hosting workloads. So therefore, they would have to function as a standard transport node with a TEP, so that they can service east-west traffic, even though technically the virtual machine edge nodes is right on them. So it just sort of be kind of a bastardization of communication on the same host for anything going in and out of a workload on it, in through in the edges on the virtual machines, virtual machine nodes.
Yes.
So we're going to assume the transport nodes here are strictly for the purposes of edge servicing. And then for the edge itself in the red here, and then the green is going to represent our hosts. And then I'm going to draw it out in more detail here as we go through our east-west communication. And the guide actually does a fairly good job of graphically explaining all of that communication. So we're really pretty much reiterating what's in our design guide, because our design guide is almost a tutorial guide. So if you were to not understand much about NSX and just read the design guide with a good understanding of just networking in itself, you'd have to have some basis of it, of course, then the guide is just going to tell you how we do it from a data plane perspective, because we already mentioned the control plane is automated by NSX in gathering up what needs to be provided for the ARP resolution, endpoint resolution for the MACs to the TEPs and things of that nature. And then the routed information obviously is going to be gathered at the edge, done by the virtual machine edge nodes. And that's going to be done through some routing protocol, static, BGP, OSPF. And then the control plane distributes that knowledge throughout the rest of the NSX infrastructure of whatever is necessary. Normally, though, and this is a key thing too, again, that simplicity factors are key value here. We're kind of the stub. Now, we can be a transit network where we can go and circulate routes in and out of one external environment, et cetera. But technically, we're a stub because we don't really play well as that transit network, because we don't want to do that. In fact, if you do that, in some cases, you probably did something wrong. All right, because we really don't want to do that. We prefer to be just the endpoint of all communication, so that when you talk about a downlink, which is what we refer to a segment, all right, and I think the guide kind of goes through the historical nature of nomenclature of what was actually called something previous to this, et cetera. But the downlink would be our segments off of our T1s, right? And they're also called LIFs. So you'll see LIF sometimes written in there. That's logical interfaces, okay? So when you see it off of in that regard, recognize that we want what's off of the T1s to be the endpoint, and anything going up north of that or east-west of that on another T1 or on the same T1. And we say the same T1, we draw these T1s like this. Recognize that when I draw it like that, or if I draw a T0 here, okay, and then I'm going to start using different colors for the T1. So I'll have a T1 here. All right. All right. Obviously, I probably should have circled this one here just to keep things uniform. And then I'll have another T0 here, or T1. Okay. Now, we stated that these are abstractions that represent the logical nature of what they are performing. So this is either the distributed servicing or the north-south servicing, as that would be on the edge. And these represent two separate T1s. So therefore, I'd have to draw in, I don't have enough room over here, but I could draw in another yellow one here, and that would represent another distributed, routed, east-west connectivity of segments for likely another tenant. In other words, something I don't wish to normally route with this tenant unless I want select elements to do so. And although my firewall could probably provide that in a security sense, I might wish to just create a separate routed table instance, another virtual routed table. It's a VRF, a VRF, virtual routing and forwarding instance. And that would be represented by another T1. So another T1 doesn't necessarily imply a VRF. It can be, but it doesn't necessarily imply that it has to be. But the idea is that I would want some other tenant maybe to have its routing managed separately. Now, the beauty of this is it doesn't really cause any great deal of overhead. It just causes more operational overhead if it's unnecessary. So if I could just put them all on a single T1 because it's technically a series of tenants that can commingle from a routed IP's perspective, and I don't really care so much about that, and I can use security to disallow communication where this communication should not be, then I would prefer to just mesh all of them together in that one T1 because it can hold thousands of segments. There's really no need. So in other words, I could draw tiny little segments off of this T1 here, and each one of them would just be other logical IP domains that are connected off of this T1. But if I want this T1 to represent another virtual routing and forwarding instance, then my T0 here is now providing tenant services to obviously the default tenant, as well as all of the additional tenants that I would wish to add into the environment. And each of them represents their own IP forwarding table. So that's something very good from a design and use case understanding. Our topic today will stick with a single VRF.
Okay.
We represent two T1s. It's just we wish to, for some reason, keep a segregated segment space for the logical elements that are crafted off of that T1 for whatever reason, and manage them separately. Now, obviously, you shouldn't create complexity if there isn't a necessity from a use case perspective. So it is strictly for example's sake here today, not for instructional purpose on how to design your environment. All right.
Yes, of course.
All right. I should say it is for instructional purposes, but not how to design the environment, just instructional knowledge. Very often I go back to my Novell days when I used to teach Novell, and people are here going, Novell, what the hell is that? Well, if you're too young or you were born like recently, then, screw you. Okay. So.
Wow. Damn.
No, I'm just kidding. I meant the fact that you're obviously young and, that's good for you. but my only point being is that Novell, and when I was teaching it, and we talk about vol 1, vol 2, and vol 3, et cetera, for the data volumes. Oddly enough, we only did that for instructional purposes to make it simple to state while we were teaching. You'd go into a customer's office, and sure enough, you'd see vol 1, vol 2, vol 3, but you're like, no, you should name them after their purpose or something. Give them a labeled value. So same thing here. This is really for instructional value. This is not for technical design value. All right.
Yep. Okay. Makes sense. So, and by the way, let me just make a note. If you were just born recently and you're watching this and understanding all this, good on you. That's pretty fantastic.
That's right. Well, my son, he's just learning now. He's going through his Network Plus, and now he did his Network Plus. He's doing the Security Plus. He's going to go get his Cisco cert, because we were talking about that, Andrew, earlier in the day. And the idea being is that to get a technical knowledge of networking is not a bad thing, because we need a physical infrastructure, because we operate a logical service infrastructure over that physical infrastructure.
Of course. So do you want to highlight any other things before I go into the evil lab?
Well, what I want to talk about is this. Okay, now we talk about this connection here and we draw these lines, right? We should actually kind of label what some of these things are. So as we mentioned before, this is this could be called a LIF. All right. This could be called a segment. All right, sometimes called a downlink, depending upon the age of the documentation. All right. This is called a router link.
And that is just to highlight the inter-tier. I'm sorry, the inter-tier, tier 0 to tier 1.
It is, right? Yeah, router link. So this would also be a router link too, just so we know that. Obviously, correct. And then this would be, we would have an uplink here.
That's your external connection.
Uplink external connection, where we would have an SR, okay, for that interface. All right. Now, what we should note is that in this T0, and the reason I'm going to specify this is because this is an important component to be aware of. In this there, we technically have an SR and sort of a DR in it. Remember, we mentioned that there's in these tier one, even the T1, by the way, but we don't really specify unless we start running services off the T1. So for the purpose of this discussion, we're just going to refer to just the T1 as a DR purposes, no SR at the moment. But in the tier 0 itself, when we talk about it, remember there's an east-west component as well as a north-south servicing component inside of it. And then, of course, those are distributed among the hypervisors, as we noted. But the SR lives only here. So the SR lives only on that edge when we speak to physical connectivity. So even though there's a tier 0 distributed component in each of the hypervisors inside of the entire infrastructure, there is no SR component on it, right? And
that's the DR. That's the DR of the tier 0, if you will.
That is the DR of the tier 0, correct. So we have our router link here. And what is important to note about this is this one is also an auto IP segment of 100.64.0.0. All right. And then the links in here will automatically get an IP in that range.
And that's going to be important for the viewing audience because they are going to see that live.
That is correct. And then inside of the SR to the DR, there is another, backplane connection. So here's our backplane. And that one is connected through a 169.254.0.0. All right. And that one is the backplane connection between the DR and the SR of the tier 0 itself. And you're going to see that, again, that's auto-plumbed in connectivity. We do use it. And why it's important is we utilize these links in order to direct traffic within the logical network of NSX so that NSX knows so that something on this logical interface segment needs to get to, let's say, another segment off of this one we drew over here. Well, then it's going to be directed by a route value that'll say, in order to get to this, you're going to get to the IP address of the next hop of whatever is the IP address of this router link connecting into the T0. So an IP coming into the gateway off of this T1 is going to actually get the T1 itself on that hypervisor is going to note that in order to get to this network, it's got to get to the next hop of the IP address of here. So in other words, we follow standard routing mechanics. We're not making any new things operationalized from a routing perspective. We just automate a lot of what you don't have to correlate or coordinate, I should say, not correlate, coordinate. So.
And I think so. Let me highlight a couple things here because I think that there's some interesting points that you have just put out there that I want to touch upon, and I know that you're going to want to add on to it. Number one, all of this stuff is done by clicks of buttons and without you having to do any of that. All those router links, all the backplane links, all the things that tier 0, tier 1's connecting off to each other. All that's done automatically. You don't have to worry about that. You create those components and it just happens. Another thing that you might ask from a networking perspective is you're noticing that it's very Clos-like. You have the T1s that are connecting up to the tier 0s. We're talking about SRDRs, but you might be wondering, well, why don't I have a tier 1 directly connected to another tier 1? Or why don't I have a tier 2 or something like that? You don't need it. And another one of those important reasons is, remember, the DR components that are spread out between all of the different hosts. Remember in the previous discussions that we had, where if traffic were to come in on the tier 1 that's in blue on the left-hand side, going to VM number 2 on the tier 1 on the right-hand side, and they're on separate layer 3 segments, the routing is going to happen locally at that hypervisor because that lives in every single one of those hypervisors. And then it's going to be a tunnel. It's going to use the tunnel endpoint connection to send it to the host where that green tier 1 lives, and then finally do the last bit of the switching to get to that VM2. There was no reason to interconnect them. It's one hop away always. Everything's happening. Everything's working just fine, and you didn't have to worry about that. So there's no reason to be able to have those tier 1s connected directly to each other.
Right. So what I want to do here is make some minor adjustments to my drawing here. So what I want to do is I want to remove some of what we talked about here so that we can talk about what you just did. You just gave us a specific type of communication that occurs on the host itself. So
and real quick, we had a question. So Nico asked, backplane equals intra-tier transit link.
yes,
Yes, that is. I had to think about that. Yes, that is true. Intra-tier.
that is correct. Yeah. So what I wanted to get rid of is the SR here, because when I drew this here momentarily, I started to realize that this could have created a little bit of confusion. Again, if you're seeing this for the first time, that would be a problem. You're seeing it for the 30th time or the 4th time and just trying to confirm what you understand, that it probably wouldn't have been a big deal, but it would be for many people. So this would exist on this host, for instance, as is.
Mm-hmm.
That's why I removed the SR, because remember I told you there's no SR on these hosts here unless they're performing the edge servicing to the physical environment for this particular SR that we're talking about here, the SR of our chosen usage in this discussion.
Correct.
So what Andrew spoke of is that if I had 2 tier 1s noted here, all of this routed and switched connectivity would occur on the host, never leaving the physical host. So if this virtual machine wished to communicate to this virtual machine, all of the connectivity could occur on this singular host if this virtual machine and this virtual machine were hosted on, let's say, and let's call this ESXi host number 1. All right, so he'll be number 1. All right. And this will be ESXi host number 2. So Perfect. This is number 1, right? So if I had those 2 VMs on the same host, even though I've got a switched segment, I've got interlinks to another DR component here of the tier 0, all of this routed and switching occurs in the, again, now the backplane here is referring to the backplane of the physical host itself, no, not the backplane nomenclature of the tier 0 tier 0 DR of the tier 0, sorry. So anyway, that's something just to be aware of. This could occur on the same host. If this virtual machine was hosted on ESXi host 2, and this was on ESXi host number 1, then the entire routed in value set of information would occur on the source host. So VM1 is communicating to VM2. All of the routed nature of what the packet would undergo in transitioning, let's say these are physical routers, for instance, right? And they're hitting router hops inside of the environment. And you know, in the Ethernet frame, the source and destination are constantly transitioning between each of the hops inside of the network itself. And of course, the IP header is getting decrements and things of that nature for time to live, et cetera. And anything else that may have to transact would all occur at the time it got to this point here. And then again, at this point here, there's an ARP value that would have already been determined because of what we had just spoke about, how the control plane manages the knowledge of the MAC to IP values of our virtual machines, as well as the VMs to the TEPs. So it would know it was on the same host. So that way, then this could all transact on the same host in my first example, or it would transact on the second host. And if it would have to transact on the second host, when it got to this stage of the appointment of the communication here, that Ethernet frame would obviously have the source MAC of the T1 here, which, by the way, the source VMAC is going to be the same. And our VMACs on all our T1s are always the same. All right. So the source VMAC would be the same on this T1 here for all of its segments, and there'd be a source VMAC that's the same on all of the interfaces on this T1. Anyway, that source VMAC would then have a destination MAC of this virtual machine, and that would get encapsulated, of course, in an IP frame. That would, it would be part of the encapsulation of the IP frame that would be communicating to this virtual machine. And at that point, it gets encapsulated in the TEP. So let's say this is a host here. The TEP would then transit it to this host. This TEP would de-encapsulate it, see the Ethernet frame we just spoke of, and it would see that source MAC of the T1 going to the destination of the virtual machine. And it would note that when it looked at its tables, that's off a particular LIF, and it would go ahead and dump it on the LIF. So the virtual machine 2 would then receive the frame. So all of that is transacting on the source system as far as the routing, and the reverse would occur in the exact same ideal, just in an asymmetric fashion, meaning that when VM2 communicates to VM1, and again, both of them are on separate hosts, all of the routing happens on the source, so that when the host here has to transact and communicate it to the TEP on ESXi host number 1, it would then send it based upon the Ethernet frame that's being encapsulated in the tunneling communication between the two hosts. The Ethernet frame would have this source VMAC going to this destination VM. And then, of course, the IP header showing this IP to this IP. And then that gets encapsulated in a Geneve overlay tunnel, and then it gets transacted between 2 to 1. So it's all very simple. I think what you should do now is show that asymmetric communication that's found inside of our guide.
Sure. Yeah, I can do that. Let me pull up the guide right now and we can have a discussion about it. Here we go. And let me share this to the stage. So the asymmetric guide, I believe we're talking about.
You have to get to the 2-tier routing one.
The 2-tiered routing one. Yep. Here's the 2-tier routing. And I believe we were talking about. No, not that one.
No, that this describes all the interfaces.
This shows the logical view of what we're talking about here, how everything is put into each one of the hypervisors. So in this case, you have hypervisor 1, hypervisor 2, and you can see that in this 2-tier, the tier 0 DR and the tier 1 DR and the tenant 2 tier 1 DR all live in hypervisor 1 and hypervisor 2. When it's in a singular ESX host or a hypervisor, each one of these steps is happening within the hypervisor. Nothing's going to be Geneve encapsulated. Nothing's going to go through the TEP. But if we were going to go to VM number 2 that lives on a different host, you see all the steps that are happening here. We're actually doing it's going to the tier 1 tenant. It's making the route decision inside of the hypervisor number 1, and then getting ready to go out of what would be tenant 2's tier 1 DR. But now, since it doesn't live on that hypervisor, it has to use the TEP to be able to send it over to the other hypervisor. Now, the good thing is it knows about this logical topology as well. So all it has to do is send it over to the hypervisor, and it knows that essentially all these steps have already been taken care of. And now it just needs to take over the portion of what would be the switching portion of sending the traffic to the second VM and completing the communication.
Right. And what should be, again, noted is that we still follow standard routing mechanics as far as how this is handled at the data plane level. And we do this at a very high performant nature so that all of this routing, if it was on the same host, for instance, we could do this at nearly 100 gigabits of speed on the same host. If it's obviously between two hosts, well, then we're going to be left to the limits of what the physical interconnectivity we have, and of course the usage of the offload so that we can leverage that near line rate communication inside of the physical infrastructure. So if we have 10 and 25 and 40 gig links, we can leverage that near line rate capability to give you similar performance between two TEPs inside of an NSX network. So as you noted here, anything that's east-west will never go between more than two hosts ever. Obviously, then with a single switch hop or I shouldn't say a single switch hop, because it could, of course, be routed because the endpoints inside of the physical infrastructure could have routing versus switching, depending upon the nature of where the host reside at. So if the host are two racks, obviously it might ping pong through a leaf, spine, leaf, etc. But again, only two hosts had to have the communication required to transact that east-west communication. So when we're talking about designing and use case value with one NSX, we're simplifying the physical infrastructure because the physical infrastructure is a backplane, large pipe plumbing that is static. It's resilient because it's static, and you concern yourself with only providing the necessary IO and not having to do anything other than just maintaining the nature of communication on an east-west basis into the border leaves, and then, of course, any north-south communication in and out of the data center that's required by your environment. NSX provides all of the smarts at doing the network communication, and all of this is transacted in a very simple manner when we talk about operationalizing it, which we're going to get into a little bit. I think we're going to still probably talk about right now. I think what we want to do is start to show you a handful of things at the CLI layer. And before we do that, though, we should note one thing. When we talk about the routing protocol, so we'll say right now you're using, let's say, eBGP. Okay, and you're communicating to two switches upstream, or we'll just call it a switch right now upstream. All right, so a layer 3 switch, and to some SVI in that layer 3 switch. We're going to be, oh, sorry, eBGP, I can spell.
You kind of looked at it like you were a little confused there.
When I was looking, I kept thinking, I know that looks weird. Okay, so there's eBGP communication here. We set up inside of the SR a series of knobs that we turn off or turn on, and then tell the BGP services what we wish to plumb forward or advertise inside of our adjacency with that physical switch. So we specify, do we want the connected routes? Do we want to add any additional static routes? All right, is there another routing protocol that we need to dump information into that table, etc.? There's a series of items that we can select. And at that point, then, as we add additional logical segments, this can all be done in a very simplified manner so that when you add that logical segment, assuming it's not NATed, and even if it is, it's obviously going to happen in an automated fashion. But if it's not NATed and it's an IP domain that's added into it, it's going to get plumbed and then advertised into the physical infrastructure through that adjacency, that neighbor relationship. This makes things extremely simple from an operational perspective so that it scales very easily, so that when I deploy new apps, and we talked about something about VPC, I think weeks ago, right? And I know you had a session with VPC with one of our other experts inside of our PM team inside of VMware. And he probably, I think it was Thomas Vigneron, if I'm not mistaken.
Yes, Thomas, yeah.
And Thomas. And he probably told you the simplicity at setting up at that VPC. Well, remember, that simplicity is based upon the infrastructure routed services that have already been set up in a very easy manner. And all he's doing then is just setting up some simple tenant that allows you to just instantiate new segments and do nothing else. And they're all routed and connected because everything is all automated in the control plane of NSX for you, with any variances that you have predetermined through other configurations that you desire to change. So if I don't want certain IP prefixes to be advertised, you can do that. If I do, so be it, they can be done. And even at the time I create the segment, I can always say, I don't want that one to be advertised. So there's ways to make certain that things are not automated just based upon some preset values. But the preset values obviously allow you to scale your operations on a simplified manner, because that's the whole point. You want to be able to craft a design that allows for simplified scaling without having to do a lot of work unless you have one-offs. And then we allow the design to also bend to those one-offs whenever necessary.
So, all right, I think that we have done a fantastic job of setting the plate. But now the question is, how do we actually see all this stuff? Well, all right, we're going to go in. So I'm going to go into the very world famous evil lab here. So let me go ahead. I'm moving it over so I can not look like I'm always constantly looking up on my screen. We'll share the second screen. All right, so now it's right in front of me. So, all right, so first off, what we're looking at here is just number one. I have a very large lab and a lot of things. So let's go into the NSX side of it. So if we're looking at this, we're talking about number one, the edge. Now I have a singular edge that's deployed in this right now, this fabric, because we wanted to keep things simple here as we're going through the command line. Now, let me be very clear. We're showing the devil in the details, if you will. We're showing all this. But a lot of times, unless you're into some very in-depth troubleshooting, you're not really going to need to go into this CLI. We just want to visually show you exactly what's going on. Now, the edge that we're looking at principally here is this lab edge number one. This edge bridge is going to be for a future show. So, you know, a little sneak peek there. But we're talking about lab edge one. So how do we see the DRs and the SRs and all these things that we've been talking about? Well, what do you say we actually pop into one? So we're just going to go ahead and enter into a putty session onto this guy. So we're going to SSH into him at 144 as management IP is, and let me just log in. Now, remember, when you're configuring your NSX and deploying your edges, you have to set your username and your passwords and things like that. Obviously, you're going to have admin and there's audit and all these different things. So it's whatever you set your username and password to be able to log in into your own edge. I've already set this edge up, so I have the ability to. So now that we're actually in the edge, how do we go and look for some of these components? Well, they're logical. We were talking about logical routers. Everything is done here logically. So it's probably going to be something like logical routers. So here we have in the edge, we're talking about our SRs and our DRs. We've been talking about the tier zeros and the tier ones. In this case, because what we have here is an SR functionality in both the tier 0 and the tier 1, because remember, the tier 1 SR by default would not be created if I wasn't doing some kind of stateful service. In this case, in a future thing, I'm going to be doing something with edge bridges and doing it on the live stream. I just happen to have that created. So an SR tier 1 was created because of that edge bridge functionality. Now, we're not going to talk about that. We're not going to actually get into it today. That's for a future show. But I just want to show there's a reason why that was created. If that wasn't done, there would purely be a DR tier 1, and that's it. So how do we get into one of these logical routers? Well, there's a couple ways that we can do this. If we wanted to show, for instance, the SR tier 0 is created because we have a BGP connection that's created. So let's actually prove that out right now. Let's go into the tier 0 and let's show that BGP connection that's going on. So we have interfaces, external connections that Paul was talking about earlier. We have it going over a VLAN 1010 that I created in this lab that's going to a leaf switch in a Kloss architecture that I have built out. We have a BGP neighbor that's sitting there. It is successful, showing that the relationship is up and running, and we're good to go. So now, how do we prove out all of that stuff that's going on in the SR? All right, well, number one, let's prove that BGP is working. So if we were going to do the get logical router, since we've already looked at all of our logical routers, let's look at one singular logical router, which happens to be this SR on the tier 0. Now, there's a plethora of things that we can do here. We can look at the interfaces. We can look at neighbor relationships. We can look at BGP. And in this case, we will be looking at BGP and neighbors. So when we bring up the neighbor, this looks very reminiscent to other style configurations that you look at if you're looking at it. So you can, other different types of network operating systems that are out there from different vendors. We're seeing, BGP relationship is up and running from an external link. We have it established, all these good things. So we can look at that. Now, what if we want to get into the SR itself? Now we're looking at this from a UUID, and we're going to and getting the information from the SR. But what if I wanted to log into the SR? Well, let's go back to those logical routers. And you heard Paul talking about a little bit earlier that VRF. Well, each one of these are assigned a VRF number if you're looking at this. So, for instance, right here, our SR that we were looking at is VRF2. So we have a command in here to actually enter into that VRF. So now we're inside of the logical router. Now, remember, this SR lives in the NSX edge because it's stateful. The DR functionality lives in all of the different hosts. Now, we're going to talk about the routing table in this. Actually, first off, Paul, let's look at the interfaces first, because I think that that's the more interesting thing. So what we're going to do is we're going to do a get in interfaces. Now, Paul, what am I looking at here? So I know you're probably going to have a little bit of a hard time seeing it from your screen. So the first thing I'm going to show is I'm looking at the downlink. That's the 164.00/31. And it says tier 0 to tier 1. That sounds pretty familiar. Let me highlight you again, because that looks pretty familiar from your drawing.
Now that's right in here. So that's this link between here. And remember, we use that link so that we can express to the forwarding table information how packets need to transact in an east-west nature in NSX. So it is there for a purpose. It serves a specific purpose. There'll be another one. That'll be that inter SR link, or not intra-SR, intra, the transit link that's on the backplane of the T0. Sorry, you got to make sure you say that properly because we do have something called an inter-SR that's different. So that intra-transit link that is inside of the T0 between the DR and the SR component, so that when something is communicated, eventually gets its way to the T0, it does it, all right, through that router link that we're obviously going to have for the T1 and the T0, and then you have the T0 going into the DR here on the T0, and then the DR here has to transit it up to the SR, and that's going to be through that backplane linkage that we mentioned before. And that will provide then the understanding of the forwarding table will say, I'm sorry, that will provide for the forwarding table to dictate how it will, of course, egress out of the environment. And then, of course, which node that it actually was placed upon is an ECMP decision that we're not going to get into today. We'll talk a little bit about ECMP probably at our next one. I think that's the last one we'll have to do before we can start getting into just some design elements. But at the present moment, it would then, of course, been decided upon which virtual machine edge node, so that the flow would go in case we had an active T0 setup with multiple virtual machine edge nodes and multiple uplinks, up to 8 in our current ECMP array that we can provide. And it would have then transacted northbound. But the key thing here is the MAC values that would have been inside of that frame had already been composed and transacted on the originating host before it was sent across that tap. The only thing that the T0 had to do here was just send it from the DR to the SR, and then it would just, of course, flow out the uplink. All right.
So, and looking at that backplane port, here we have it right here. I'm actually looking at it. So the 169.254.02/25. So that you can actually see its name, BP-SR0- port. It's the port type of backplane. So it literally does show you in the CLI exactly what this is for and what it's doing.
Remember, we said that there were a couple of things that you had to make a decision at the moment of the creation of that T0. Now, there's a few things that you decide at the moment of creation, but the two things you have to decide at the beginning is those IP address spaces for that backplane and the IP address, well, not for the backplane, but the IP address space for the router link. And then there's something else that we'll talk about later, but that router link IP address prefix, you have to decide whether you'll accept the automated one that's 100.64, and it complies with some RFC 65 something or another. But there's an RFC that it complies with that was meant to be used for some automated purposes like what we are doing. So we are actually following an RFC in using that in an automated fashion. If for some reason it conflicts, could you have that someplace else, which you may, that's fine. It would be weird that it would conflict, but it could, because remember, it's really just going to be used inside of here. So the only way it could conflict, it would be something that you were using in the physical realm or in your environment, you have to send it to, because nothing on the internet is going to use that prefix. But you might be using it for something else inside of your own environment, or you, for whatever reason, created another logical lift with that IP address segment for some reason whatsoever. So
yeah,
conflict, it would be rare that you would do so.
And we're actually looking at it right now, Paul. So we're looking at the internal transit subnet, which is 169.254.00/24. The tier 0, tier 1 transit subnet, which is the 164.00/16, where it's pulling from that range as we create additional tier 1s, and it would create those additional connections. And then the we haven't talked about this, but the inter VRF transit subnet, which is very close to 169.254.2.0/23. And you can actually see these links that are created, the router links that go off. So in this case, since we have a singular tier 1 that's off this tier 0, you could see the 164.00/31 range that it's using to be able to create that link between the tier 0 and the tier 1.
And what, again, it's important to note that all of this is auto-plumbed for you. And we have to still show you, though, how this provides an additional value. And that, I think we can get to next, is you're right there. I think we can start talking about what gets placed into the route table. So maybe you want to show them the route table.
Sure.
Yeah.
That was actually my next move. So like we did in the previous area where we're looking at the UUIDs and then we can get information from it. We're actually in it and we can do much the same. We can go ahead and look at the route table here. So let's go ahead and hit route. And this is going to show routing on the SR. Now, there's a lot of information that's here, so don't get intimidated by it. But what you'll see is, number one, like we have, it's pretty, once you look at the flags here, you can kind of start to decipher what's going on. So for instance, our default route, we have a tier 0 and an S for static. So a tier 0 static route, you can see that up here in the legend, saying anything that's going out is going to go to the next hop of 10, 100, 11, which happens to be our leaf switch on that uplink that's there. And you can correlate the interfaces to the actual uplink name so you can see all that information. We also have tier 1 directly connected routes that were learned from the tier 1 and its next hop, if you notice. So this tier 1, this 10.10.50/24 lives on that, like I said, tier 1. So its next hop is going to be that router link 164.0.1, and it's going to use that downlink interface to be able to reach that. So Paul, let's talk a little bit more about how that auto plumbing is working immediately, and the fact that we specified in that tier 1 that we want to redistribute those connected routes to the tier 0, and we can see the proof in the pudding in the routing table.
Right. I also note that the tier 0 and the tier 1 is sort of a combined route table, which is why when you did that, you actually got routed knowledge of both. That was done a long time ago in NSX's heritage as it grew up, where we decided to place them in the same route table because it was going to allow us to extrapolate to new services such as EVPN and certain types of VPNs and things of that nature, and make it much easier then to provide those service capabilities with routing involved in each of those, so that decisions can be made at the various tiered tenant localities that those services would be instantiated at or for the purposes of, such as EVPN using multiple tenants going through a default EVPN connection going outside of the network itself. So all of these kinds of things were done at a time, or excuse me, were modified at a time knowing that we were going to make adjustments to the way we would want to route information inside of the environment, but it doesn't change the nature of how things route. It just explains why you see a combined route table value there when you went and looked at the routed information.
Yep, exactly. And, just continuing on here, now that we've talked about that, is, we see the rest of the tier 0, like directly connected routes and things that are there on the tier 0 and the tier 1. But here is those very special ones. So first off, that tier 0 directly connected, which is that backplane connection there. So there's the proof in the pudding yet again that we have that 169.254 range, and it's a directly connected. And that's that backplane communication, Paul. We want to talk about that one more time?
Well, it's just the backplane communication between the DR of the tier 0. So if we were to draw that back in, that would be that SR component here. And then the backplane would be that connection here. It'd be the 169.254.0.0, of course. And that would be the interconnect between the DR and the SR of the tier 0. And that's obviously the last hop. So there's, again, some routed knowledge that must be required for us to follow in order to get from those components. So we're not doing anything in a completely proprietary fashion. Obviously, the way we provided our east-west and north-south communication scheme is a little bit, but the actual Ethernet network routing servicing is not. So therefore, the mechanics of that still follows the same paradigm, and it's easily distinguishable on how that occurs once you understand what they are.
Excellent. And so we have 7 minutes left. So what I want to do before we call it, because we're approaching the top of the hour here. So there's two other things I wanted to highlight here. So number one, Paul, I'm going to hop out of this tier 1, this SR and the tier 0, I'm sorry. And let's go back to the get logical routers, because what I want to do is I actually want to show a DR that's out there. So let's go to the DR of the tier 1. So let's go into VRF number 4, it looks like here. So now we're in tier 1 DR. And if I start to look at this, I notice look how there's no route. There's a get and but I see no route, but I see forwarding. So let me go ahead and actually do get forwarding. Why is there a difference if I were looking in the CLI of I go to a tier 0, I have a route table. If I go into a tier 1, I only have a forwarding table.
Well, because of the nature of how the control plane is transacted in NSX, we only have dynamic routing at the edge in the tier 0 itself. Dynamic routing does not occur in any of the other components because you don't have to administer it. And that's all in that highly automated fashion that you can coordinate on how that occurs due to the way you construct the tier 1 in its communication to the tier 0, and what do you wish to populate the tier 0 route data, route knowledge, in order for it to know what it should be forwarding onto its neighbor in whatever routing protocol you're using here. Static. I think static is what you're using in your environment right now, Andy.
I am. Yes.
Yeah, you're not using eBGP because obviously noted by the route table using a static value to get to something external. All right. With that in mind, that means how do we garner the requisite knowledge so that these tier 1s can operate in an appropriate fashion, as well as so we can go back and troubleshoot them. So what we do is we transact in the control plane a FID table that's really just a forwarding information base that is populated by the control plane of NSX. So that NSX, remember we told you there's multiple services that are in the NSX manager appliances, and one of them is that control plane, and that control plane then populates the tier 1 forwarding information base across the entire infrastructure in an automated fashion, and just plumbs it with what essentially will become just rewrite knowledge that is necessary for the packet forwarding process to occur on a high performance east-west basis. They're not looking at a route table. They're not looking at transactions that have timed out or not. All of that occurs whenever NSX garners the necessary information and then has to, of course, populate the rest of the east-west forwarding information base, and does so. So you're not concerned with an OSPF or a BGP routing protocol instantiation of some sort of remnants of it over here. You're concerned with if something is missing here and how to get to that external one, you go to the north-south source of where that information should have been received. And then the NSX control plane would have automated its population in the forwarding information base of all of your other hosts. So that's what you're looking at there. And that's important to know. So the tier 1 DR services is a forwarding information base. The tier 0 SR servicing is a dynamic routed set of, well, it doesn't have to be dynamic routing because you could acquire it through static routing, but it is something accrued through a routing protocol.
Excellent. So that's a great explanation of that. And the last thing I wanted to show, and we're only going to touch upon it, and we're not actually going to dive into it. We're not going to get into it because I like to leave a little fun teaser. And this was something that as I was going through the lab, I just wanted to visually show people. So we're even going to put away that that edge router. So let's talk about actually from a host standpoint. So this is actually pretty cool, and I like showing this stuff off. So in my VCSA, so I have my vCenter that's sitting here. Let's dive into one of these hosts. So for example, let's go into, I'm going to be looking at this Web 01 here. So Web 01 is living on, looks like 10.10.144. That's one of my hosts. So let's SSH into that guy and let's go check him out real quick. So let's go 10.10.144 and let's dive into him. Let's log in. And in order to be able to get into the NSX CLI of this, you just type in simply NSX CLI. Now, a lot of the same commands are going to be here that you would see. So get logical routers and switches, and let's just look at logical routers. Now, the first thing you're going to notice is, hey, there's nothing. How the heck is there nothing there? We were talking about DRs and SRs and stuff like that, and they're distributed, but I don't see anything there. Well, all right. Well, let's actually, because there's nothing there. There's nothing on right now that's actually participating. There's nothing on a segment, nothing going on. So let's go to that Web 1 and let's make sure that it's on one of our segments. In this case, I have a web segment created in NSX. Here he is, web on our overlay transport zone. This is a host that's prepped with NSX, and he's on there. We're going to hit OK, and then we're going to go ahead and power this guy up. So now that Web 0 is starting up, and it's going to be put on that segment in the NSX fabric. And now we were going to look back, and boy, I hope this doesn't make me look like an idiot. Oh, it didn't. Oh, there it is. So there is that DR component. Now it's there, and we can actually get into logical router, and we can start looking into this thing again. So let's go ahead and show this. And then yet again, we can start looking at the forwarding table again. There's the forwarding table of this DR. Now that we had a VM that was instantiated on this and now participating and living on a segment that's on a tier 1, this host now has all that information and it knows what to do. And if it needs to go out to another host, it can do all the local routing and then it'll use its TEP and take it over either to the edge or another ESXi host where that traffic lives. Isn't that cool?
That is, yeah, and that's super cool because that applies across the board in how resources are properly expended inside of NSX in order to manage that control plane. We talked about it before that virtual machines MAC values have to be known. Well, obviously they get populated and known by just vCenter itself whenever you turn something on, but then NSX of course learns that, acquires it, maps it to a TEP, tells the rest of the world about all of that information. And as you just noted here, we also do that with the forwarding information base because of the DR component that would now be present, or I shouldn't say present, but is now activated, probably a better word, right? Activated in that host so that NSX knows now to properly maintain its forwarding information base. So the control plane populates that in an instant, as you just saw. I mean, you typed it, went back and forth. It was there. Obviously, that's a handful of seconds, but it was doing it behind the scenes in milliseconds. So that's a fantastically fast and expedient way of things getting done. And what we should note is that by the time the virtual machine came up and was actually functioning to receive something, that DR was populated with the necessary knowledge. So it's not like it's something that has to happen in a cascaded fashion. It's actually occurring almost simultaneously in retrospect, because when that virtual machine's coming on, it already knows that it's going to live off of this segment because NSX isn't waiting for it to actually register to the segment or anything like that. It just knows that it's going to reside there. And at that point, we're beginning to populate the information that's appropriate for that host of that segment. And then MAC value is also getting populated to the TEP, et cetera. And that's getting also announced and spread. So these are things that people should be aware of, that NSX is doing at a very efficient manner behind the scenes and handles that for you, so that your responsibility is more about how you should design your world to make it even simpler as you begin to grow your virtualized network.
I think that's, the takeaway there is like, look, while we have gone through and there's a lot on the light board that's there and a lot that we showed in the lab and a lot of the technical details, we got into the nitty gritty and had a lot of long discussions. We're only going through this is because, understanding is key and understanding is power, but it's so simple. All we're doing is literally just going click, click, creating tier zeros, creating tier ones. I mean, it's super simple, and understanding this is great and it's fantastic, but you didn't need to know all of that in order to be able to deploy and to operate NSX. We're just tearing off the covers a little bit just to be able to show you what's there, but this is all done for you in the background. We just want you to understand it.
Right. And we skipped over because just time just doesn't permit us to. I think you and I try to jam in as much as we can in this limited time that we do have together. But we're skipping over operational tooling, the UE itself that could have exposed a lot of that route knowledge. And you could have clicked through various localities to find some of the exact same route knowledge you found at the CLI. There's a handful of things that are a little discriminate, maybe a bit better at the CLI to some extent, but in essence, you could have found all of that in the UE. There's a topology table that maps out the entire network segments as well as external connectivity. NSX now provides that in an extremely explicit manner. Obviously, it can't do any of the physical stuff, but it does tell you that it's, for instance, it would say if you had 4 uplinks or 8 uplinks, it would show you, and each of them are BGP, and it would show that all of them, all those neighbors are up and running and things of that nature. So that's another cool feature. You have ARIA operations for networks that we talked about last week as well, that would give you a complete visualization of it, as well as troubleshooting, as well as control plane connectivity issues that it discovers, or data plane knowledge that you may wish to try and gather as far as what statistics and metrics that have been for various flows through your infrastructure, and then what interconnectivity require or services that are being offered within the environment. So AON offers you, or ARIA Operations for Network offers you a multitude, a plethora, if you will. I like that word.
I like that word.
Information. Okay. So, we skipped over all of the operational features that are either inherent in NSX, which are many, or the operational tooling of what ARIA Operation for Networks would provide you, from not only just troubleshooting, but also understanding the performance and scaling and the flow of communication throughout the infrastructure, inclusive of the physical, as well as security that you would be able to see. It would tell you every juncture where a firewall rule was hit and things like that.
We're already, I'm just showing the network topology right here. And like I said, we're reaching the end of the show, but boy, you know, what if I wanted to just literally add another tier 1? So I'm going to add new tier 1 right here. I'm going to call it an active standby. I'm going to hit tier 0. I'm going to specify that edge cluster being the edge cluster number 1, and I'm going to hit save. And boom, everything's already configured right there. All that stuff that we just talked about, boom, is done. And look, a brand new tier 1 is created here. Shows you the mapping, shows you that router link. It just went ahead and it subnet, it allocated a new subnet for it, a new /31, and has it there with one service. I mean, what we talked about literally in an hour, and I just added a new tier 1 and did all that stuff within 30 seconds.
Well, and if you had to add another segment, add another 6 seconds.
There you go.
Exactly. So, and technically, you could have just pushed an API button, and it would have obviously been instantaneous. Anybody can say that in any environment, but the neat thing of our environment is that the simplicity of how you can look under the covers. You didn't have to craft a lot of infrastructure dependency objects of some crazy nature to actually make any of that work. You just had to instantiate the basics of the transport nodes. And once you got that deployed, everything after that just begins to take shape in a very simple fashion.
Yep. So, I mean, I think another wonderful discussion here. So, ladies and gentlemen, next week, we're going to be talking about a couple different topics. We're going to be talking about AOB, and then the week after that, HCX. So, Paul, you've been here for 3 weeks in a row. I just want to make sure that I give you your flowers right now. Thank you so much for 3 weeks in a row, including the very first one that week being your birthday, if I remember. Fantastic. Thank you so much. I can't wait to have you on again in a couple weeks. We're going to plan something out that's even more special for the networking side. But, thanks for everything. Thanks for all of this great knowledge that you've been bestowing upon us.
Yeah, I think what will begin to make more sense of all of this too, not so much the fact that of how it works, because I think we did a pretty good job of exploring that. They have the design guide there to go back as a basis to follow along with, and they'll find that what we said here and what is said there will correlate well, and it'll sink in because they'll have it from 2 different perspectives. And then the aspect that I wanted to get to is when we start talking about use case value, we start talking about why you would want to use this in your world to deploy things. You already had one really good use case, that VPC, but we'll go into a bit more depth of various use case structures or designs so that people will have a good understanding of where NSX really excels, whether you're in a small, mid, or extremely large environment.
Awesome. You know what? I'm looking forward to that. That's going to be in a couple weeks. Hopefully we'll put that up on the public calendar. Paul, I'm going to wrap up this show. Stay on, and I'll see you in just a second. Thanks a lot, Paul.
Bye-bye, Andrew.
Ladies and gentlemen, thank you so much for joining us on the VMware Networking and Security live stream. So like I said, next week we're going to be talking about ALB. We're going to do a nice introduction of it, explain what it does, its use cases, a lot of great stuff. I'm looking forward to that. It's going to be an exciting show. And then the week after, we're going to do some on HCX. And then we have a very special guest that's coming on in a few weeks from now on the customer side. So we have a whole plan for the rest of October. Looking forward to it. We have shows that we're going to book up in November. So I'm looking forward to being with you all and having you along with me. Make sure to ask some questions. Make sure to visit NSX Tech Zone. We have so many different areas that you can learn about it. We have YouTube videos on this very YouTube channel. We also have videos. We also live stream on Twitch, and there's some of the stuff that's there as well. Thank you so much for joining. We'll see you next time on the VMware Networking Security live stream. See ya.